Welcome back, everybody. So now we're going to prove a very important theorem about ordinals, which maybe with examples we've seen so far, you were suspecting it. Is comparability of ordinals. And it says the following. Whenever you have two well orderings, which as we know, the ordinals are a special type of well orderings, like unique representatives, one of the following holds. Either they are isomorphic, or one is isomorphic to an initial segment of the other. Okay, so the three possibilities here look like either we have A and B and they are completely isomorphic, or A is isomorphic to the segment below a certain element B from B, and we get the isomorphism right there, or B is isomorphic to the segment below some element little a in A. So this theorem says that one of these three things must happen. Like one has to be isomorphic to an initial segment of the other, or they're just the same. So in a sense, this provides you an ordering among the well orderings. Any two well orderings, one is larger than the other, and we can linearly order all the well orderings. That's going to be quite interesting. Okay, so let's prove this theorem. The idea for the proof is as follows. Let's do the idea first and then the actual proof. Suppose here you have A and here you have B. They don't need to be equal. We don't know how they are. What we're going to do is we want to define this isomorphism between either the whole thing or one segment or the other. And what we do is we take the first element here and the first element there. They have a first element, right? Because every subset has a least element, so the whole thing. And we match them. Now we remove those guys, look at the least elements of the rest, and we get a least element here and a least element here, and we match them. Now we remove those, least element, match them. So on and so forth. Maybe we go infinitely match, but whenever we are, it's always a least element and least element, and we match them. Least element, match. And we're gonna go all the way until we have a full match, until we run out. And eventually we will run out. And either we run out because these elements run out and we'll have no more A, or we run out because this one goes to here and then we don't know where to map this guy, or they just match, right? This is an intuitive definition, intuitive proof, which only works once you're very used to working with transfinite recursion, right? Because A is this like infinite, it could be these huge sets. All we know about it is this property as a well ordering. So this thing about doing things one step at a time intuitively kind of makes sense, but formally it doesn't, right? Because what does it mean one step at a time when you have a set A that has a size of the power set of reals? In what sense? What's it at one point at a time? So the formality behind its recursion, the intuition behind recursion is you just do one step at a time. So let's do it. So let's start taking an element. So we define a function f from A to B union a top element. Let's say another element that is new. Let's call it T for top. And T is a new element that doesn't show up anywhere. Something. We think of it as above by transfinite recursion. And the idea is exactly what we did so far, right? So if we want to define, here we have an element T, and we want to define f of T, what do we do? And the idea is to do what we did so far. Suppose we have an element T, and we want to define its image, f of T. So then we say, well, look at all the previous guys. Where were they mapped? And then we say, well, where do we want to map this new guy? Well, we want to map it to the first position that hasn't been mapped yet, right? And that's going to be our f of T. right? And then you go to every time you take a new one, you look at all the images of the previous ones, and then you say first position that hasn't been mapped yet. So let's do that. So f of t is going to be the least element of B that has not been mapped yet. So that it doesn't belong to the range of f up to the segment of t. So it's not in the range so far for the elements below t. This is the least element according to B, right? This is the least according to B. And there has to be one. Well, there has to be one if that set is not empty. So this is if the range of f up to the segment of t is not everything. It's not everything, right? And otherwise, we don't have room, because otherwise that set is empty. We don't have room. This will be the otherwise case will be a case when we want to define it here, and the images of all the previous ones have run out already, and we don't know where to go because there is nothing else. In that case, we map it to these top elements. Otherwise, we let it be t if run f up to segment of t contains all of B. Okay, so let's see that this works. So what do we need to show? There are a few things. First, if S is less than T, there are two elements of A, and f of T is not top, then f of S is less according to B to f of T. Why is that? Well, when you define T, why is that? Well, when you define S, you define S to be the least element of B minus this range up to S. And when you define T, you did the same thing, but you took a smaller set, because by the time you define T, you have removed more things from B, right? The range is larger, right? So S is a least element of a larger set, right? Every time, so these are the sets, the elements that are left. Every time there are less things left. So if you take the least of a smaller set, you start going up, right? Essentially, that's what that's happening over there. So we get that it is one-to-one and order preserving on the domain. Another observation is that if we have that element B is less than f of t according to B, and f of t is not top, so it means belongs to B, then there exists an S less than T such that f of S equals to B. And the reason is that if you're below but you're not in the range, if this wasn't the case, it means that you're not in the range up to level T, up to point T, you're still not in the range. You're still not. If this was the case, that means you're not in this set. But if you're not in this set, then you would define f of t to be that guy, because you're taking it to be the least one. So if you didn't choose that guy for f of t, it's because that guy was already in the range. So that means it was f of s of some b for s below t. So they are kind of grow. This function, essentially what this picture shows, what these two things show, is that the function is always preserves ordering and it doesn't leave gaps, right? You don't leave any gap in here in the function. Essentially it's defined so that it doesn't leave gap. It always takes the least one that is not in the range, so there's no room to leave gaps. By the way, the fact that this list exists is because you're using the fact that B is well ordered to do this. We're using the fact that A is well ordered to use transfinite recursion. Okay, so good so far. Now we essentially have what we want. We have to show that this function is going to be the isomorphism that we want in at least one of these three cases. Case 1 is that t belongs to the range of this map F. In this case, if you look at the picture, it means that t belongs to the range, somewhere right there. So there must be some element mapping to it. Actually, and all the elements later are going to be mapped to it too. There are going to be many elements mapping to t. But there is going to be a least element mapping to t because it's a well-ordering, so every subset has a least element. And all the previous ones are going to be in one-to-one correspondence with B. So let A be the least such that the range that maps to T, F minus 1 of top. The least one that goes to there. So that means all the previous ones do not get mapped to top. So then we get that F is a bijection from the segment of A to B. Right, because the reason that A was being mapped to top is that we already had that B belonged to the range of F up to the segment of A, right? So that's exactly this case up here. And all the elements below get mapped to things that are not top because A was the least one that is being mapped to top. So actually we get, in that case, we have equality right here, right? So actually equality right here. So F up to the segment of T is equal. The range of F out to the segment of T is equal to B, and we get a bijection, and that's our isomorphism. So that means we are in this case up here. Okay. Case 2 is when the range of F is actually equal to B, but in that we already know that it's one-to-one, that it's order preserving. So in this case, we get that A less than is isomorphic to B. And therefore we are in this case. Case 3 is that the range of F is a proper subset of B. Let B be the least element of B minus the range of F, which we are assuming is not empty. But we know from our second condition right here that the range of the function F is closed downwards, right? If something belongs to the range, everybody below it also belongs to the range. That's what that says. So B is the first one that doesn't belong to the range. So what we actually get right here is that the range of F is equal to the segment of all the things below B. So B is the least one that is not in the range, right? And then that gives us, that puts us in case 2. Good. So essentially those are the three cases. Either you run out and you map up there, or you finish exactly at the same spot, or maybe you run out, you finish A and without running out of B, but in this case those initial segments are isomorphic. Cool. So that's the proof of the theorem. So now we get that any two well orderings, one must be an initial segment of the other one. And so the well orderings are themselves linear order. We're gonna see that in the next video. And the well orderings are themselves well ordered by this inclusion relation. See you guys in the next video.